everyone. You're watching the second part of the 32nd lecture for the course Mathematical Methods for Economics. We will now wrap up our discussion on infinite series. In this part of the lecture, I will summarize the results that we have developed so far, the results that I developed in the first part of this particular video. We will go through some practice questions because that's really important. And more importantly, I will provide a roadmap for you which will help you solve the questions in this topic. Okay, so what are the results that we have developed so far? And remember here, like I said in the previous, in the first part, that there's a vast literature out there and lots of tests on convergence, divergence in this topic. But nevertheless, we will stick to what you have in your syllabus for economics honors, and here we go. So let's just summarize the results that we have developed so far. Now, there are basically three kinds of series that we have looked at. Actually, let me say we have a general infinite series which will then take up other kinds of series also. So, let's be more specific first. So, we have an infinite geometric series. There, if the common ratio, we discussed that if the common ratio is between -1 and 1, which is to say that if the absolute value of the common ratio is less than 1, the infinite geometric series converges, and it in particular it converges to the sum a divided by 1 minus k. It's absolutely fine if you're using the notation r for the common ratio. So, in that case it will be a divided by 1 minus r. Here we are using k for the common ratio. Then if k is greater than or equal to 1 or less than or equal to 1, which is to say that in absolute value the common ratio is greater than or equal to 1, we say the infinite geometric series diverges. Then we also looked at the an infinite series of the form 1 by n to the power p, and as long as p, the exponent here, is more than 1, this series summation 1 by n to the power p is convergent. And our main analysis was for the general infinite series, which encompasses all the series. So, this for this series we established that, and this is the result that you will use for your questions, the problems that you will do in this topic, that if the nth term as n tends to infinity is non-zero, then we say that the series, the general infinite series a1 plus a2 plus a3 and so on, diverges. Okay. So, we will use this set of results because that's basically what we work with, and we'll use this to work on our problems. What I'll do is, because I introduced the idea of a general infinite series in the first part itself, let me first take up some problems which involve the usage of this particular criterion, and let's see how that works, just to get you to warm up with this criterion where the nth term is not 0. So, let's look at this problem. I'll be taking up most of the problems, in fact, these are the problems in the exercise for section 6.5 in Sydsæter and Hammond, and here this exercise has an excellent set of questions, very exhaustive and good questions for good practice. So, let's take a look at these questions. In this question, you're asked to show that the following series diverges. So, the series here is summation n divided by 1 plus n, and the criterion here is we take the nth term and then take its limit as n tends to infinity. Our nth term here is n divided by 1 plus n, right, and the limit of the nth term as n tends to infinity will be the limit of n divided by 1 plus n as n tends to infinity. And if you have if you have done the section on limits or watched my videos or any other videos, then here the limit would simply be given by, we divide both numerator and denominator by n. So, that will give us a 1 in the numerator and 1 by n plus 1 in the denominator. So, when we apply the limit as n tends to infinity, 1 by n will tend to 0. So, the whole thing will tend to 1, which is to say that our nth term as n tends to infinity is equal to 1. And because it is not 0, the series diverges. So, what we are trying to say here is that if we are adding something like a 1 or something which is not close to 0, then we are not going to allow the series, the sum, to settle. So, because in the limit the nth term is non-zero, as n approaches infinity, the series diverges. In part B, we have the series summation 101 divided by 100 to the power n. Here the nth term is 1.01 to the power n, which clearly tends to infinity as n tends to infinity. So, because in the limit a sub n is non-zero, the series diverges. In fact, like I said, the general result applies to the infinite geometric series, but you can also use the result for the geometric series. If you notice here, this is what you have here is a geometric series, but you should make sure that it is a geometric series before you apply the result. So, here clearly you have a geometric series because it will be of the form 1.01, then 1.01 squared, 1.01 cubed. So, here you have a geometric series, an infinite geometric series with the common ratio being 1.01, and because k here is more than 1, in an absolute sense also it is more than 1, the series is going to diverge. So, you can use either criterion here. Let us look at part C of this example. Here the series is summation 1 divided by 1 plus 1 by n to the power n. Now, here I am going to use a result which you are actually going to cover in chapter 8 of this book, but you might be already familiar with it. And here we have that this nth term, which is 1 by 1 plus 1 by n to the power n, that approaches 1 by e. E is nothing but, by definition, it is a limit. So, this is something we cover in chapter 8. It is e is given as the limit of 1 plus 1 by n to the power n as n approaches infinity. So, this entire rational function will also tend to 1 by e as n tends to infinity. And again, because limit a sub n as n tends to infinity is non-zero, the series diverges. Okay, let me give you another variety of questions, and let us now take up geometric series. Okay, so I will give you some expressions, some series, and here you have to first of all determine whether the series are geometric, and if the geometric series converge, then you will be asked to find the sums of those geometric series. Okay, so you got the idea. You have to first of all determine whether the series given to you is geometric, and then if that series converges, you will be required to find the sum to which it converges. Our first series given here is 8 plus 1 by 8 plus 1 by 64 and so on. And you can see here this is an infinite geometric series with the first term being 8, the common ratio being 1 by 8, right, because 8 times 1 by 8 is 1, 1 times 1 by 8 is 1 by 8, 1 by 8 times 1 by 8 is 1 by 64. So, you can clearly see that it is an infinite geometric series. And because this common ratio, this k, the quotient is less than 1, we can say that the series converges. Now, what does it converge to? As if you can go back to the summary of results and check, the formula is a divided by 1 minus k. So, the sum, which is what we are denoting by s, that is given by the first term, which is 8 divided by 1 minus the quotient, which is 1 by 8, and that is nothing but 8, this 8 will go to the numerator, so that will become a 64, and when we take the LCM of the denominator, we will have 8 minus 1 for the portions of the numerator in the bottom part, so that will give you a 7, 64 by 7. That is what the geometric series converges to. Okay. Here we have the series minus 2 plus 6 minus 18 plus 54 and so on. Here it is again an infinite geometric series with the first term being minus 2 and the common ratio being minus 3, right, because minus 2 times minus 3 is 6, then 6 times minus 3 is minus 18 and so on and so forth. The series here will clearly diverge, as the quotient in an absolute sense, that is more than 1. So, 3 is more than 1, or you can argue that k is less than minus 1, so the series diverges. Let us do 1 or 2 more like this. Here you have 2 to the power 1 by 3 plus 1 plus 2 to the power minus 1 by 3 plus 2 to the power minus 2 by 3 and so on. This, yes, this is an infinite geometric series with the first term being 2 to the power 1 by 3 and the quotient being 2 to the power minus 1 by 3, yes. 1 divided by 2 to the power 1 by 3 is 2 to the power minus 1 by 3. Similarly, 2 to the power minus 1 by 3 divided by 1 is 2 to the power minus 1 by 3. So, we have checked it, and here also 2 to the power minus 2 by 3 divided by 2 to the power minus 1 by 3 is 2 to the power minus 1 by 3. So, the quotient here is 2 to the power minus 1 by 3. So, will the series converge or diverge? The series will, so basically the quotient here is 1 divided by 2 to the power 1 by 3, which is going to be less than 1, right. So, the series converges. Now, what does it converge to? It converges to the sum s, which is given by the first term, which is 2 to the power 1 by 3, divided by 1 minus the quotient, which is 2 to the power minus 1 by 3. Now, let us see what that simplifies to. I have 2 to the power 1 by 3 here in the numerator, and in the denominator also, once I take the LCM, I will have a 2 to the power 1 by 3, which can be taken to the numerator to give 2 to the power 2 by 3, and here I will have 2 to the power in the denominator in the final answer. I will have 2 to the power 1 by 3 minus 1. Okay. Okay. Now, this is an interesting problem. We have this series 1 minus half plus 3 minus 1 by 4 plus 1 by 5 minus 1 by 6 and so on. This is not a geometric series. You can see here, you can't see a common ratio here. If you divide any term like minus half with its previous one, you will get a minus half, but when you divide 1 by 3 with minus 1 by 2, you will get something else. So, this is not a geometric series. You have to have a common quotient, right. In fact, this series is called an alternating harmonic series, and it has this interesting result that it is convergent. So, I am going a little beyond the course. This is a convergent series with the sum being log of 2, and here you have to be a little creative. You have these different methods that come up. This is just for your knowledge. Now, how does the series converge to the sum log, natural log of 2? To see this, we will use a Taylor series for the function natural log of 1 plus x, and then we will substitute x equal to 1. So, first let us take the Taylor series for natural log of 1 plus x. Now, if a function is f of x, the Taylor series, let me just first give you the formula in case you do not recall it. If I am taking the series around 0, around the point 0, then f of x will be given by f of 0 plus f prime 0 times x plus 1 by 2 factorial f double prime at 0 times x squared plus 1 by 3 factorial, the third derivative at 0 times x cubed and so on. And this is an exact equality because we are taking an infinite series. So, if our function here is natural log of 1 plus x, the first derivative is going to be what? That is going to be 1 divided by 1 plus x, right. Let us just get the groundwork done so that we can substitute back into this formula for the Taylor series. So, f double prime of x will be, because the first derivative is 1 plus x to the power minus 1, the second derivative would be minus 1 times 1 plus x to the power minus 2. Similarly, the third derivative would be 2 times, that minus and minus 2 will become plus 2 times 1 plus x to the power minus 3, and you can even take the fourth derivative if you like. So, this implies that f of x is equal to, what is f of 0? F of 0 is nothing but natural log of 1, which is 0. So, that term will not be there. F prime at 0 is nothing but 1, because if I put x equal to 0, I am going to get 1, right. So, that gives me f prime at 0 times x. So, I will have an x here for f of x in the Taylor series plus 1 by 2 factorial. What is f double prime at 0? F double prime at 0 would be minus 1. So, I am putting a minus 1 here times x squared from the formula plus 1 by 3 factorial, and if I see what f the third derivative at 0 is, that's going to be 2, right. So, if I put x equal to 0, this will become 1 to the power minus 3, and because I have a 2 in front, so I will have a 2. So, 1 by 3 factorial times 2 times x cubed coming from this formula here, right. So, what do we get eventually? For the Taylor series, I get f of x is equal to natural log of 1 plus x, and this implies that f of x is equal to x plus 1 by 2 factorial times minus 1 times x squared plus 1 by 3 factorial times 2 times x cube, which basically boils down to x, something, it's a very nice pattern here again. So, x minus x squared by 2, right, because this minus will come in front, x squared by 2 plus x cubed by 3, because in 3 factorial the 2 will cancel out with the 2 in the numerator, and you can check minus x to the power 4 by 4 is the next term. So, basically you get this as a Taylor series, and the next bit that you just have to do is substitute x equal to 1. So, if I put x equal to 1, what do I get? I get f of x, which is natural log of 1 plus x, that is equal to natural log of 2, which is equal to 1 minus half plus 1/3 minus 1/4 and so on. So, natural log of 2 is actually what the series converges to. So, hats off to the person who came up with this logic, and this is a very clean answer again, and this is just for your knowledge that the alternating harmonic series converges to natural log of 1 by 2. Okay. Now, what I am going to do is, I am going to give you a general question. So, if because typically in the exams you are asked whether the series converges or diverges. So, I will give you a general question. Now, how will you handle such questions? So, for this, let me lay out this general roadmap for you. Again, this is not unique, you can follow your own scheme of things, whichever criterion you want to use first. This is what I normally follow. So, first I try to see, do I have an infinite geometric series? So, if I have an infinite geometric series, then the result is very clear, so I just straight away use it. So, infinite geometric series, if I can identify in the first step, I will just straight away say that if mod k is less than 1, the series will converge. If it is more than or equal to 1, it is going to diverge, and if it converges, we can always find the sum. So, that is very straightforward. Then second step, I typically look out if the series is of the form summation 1 by n to the power p. There also we have a very straightforward result that here we haven't done the proof with you, but you have to use this result if you get a series of this kind. And here if p is more than 1, then we say that the series converges. And for the general infinite series, so you can use it otherwise also, but if you want to then as a last step look at this, then the result that we will use here is that if the nth term is non-zero as n tends to infinity, then the series diverges. Okay. So, this is to establish whether the series converges or diverges, and if let us say you are asked to find the sum, then in that case you could if you have an infinite geometric series, you clearly know what the sum is going to be. If it converges, that is going to be a upon 1 minus k, and in general you could use a method of partial sums if you have to, if the question is that you find the sum. So, let us look at some general questions. Now, here you have a series where which clearly looks like an infinite geometric series. So, you can see here it is 100 by 101 plus 100 by 101 squared plus 100 by 101 cubed. So, clearly you have the common ratio as 100 divided by 101, which is less than 1, the common ratio, the quotient is less than 1. So, the series converges, right. So, now see, this is something you wouldn't have used the general infinite series result, because that is a necessary condition, a sub n going to 0 as n tends to infinity. So, that is something you won't use, but here you can use the result for an infinite geometric series, which is absolutely the right way to do things. And here the sum would be a upon 1 minus r, which is nothing but 100 divided by 101 divided by 1 divided by 101. So, you can clearly see the 101 numbers will cancel and you get 100 as the sum. Then in the next part we have the series 1 by square root of n. So this is of the form that 1 by n to the power p, where you can clearly see that p is equal to half, which is less than 1. So the series diverges. Okay. You have part C, which is of similar flavor, where you have a series which is summation 1 by n to the power 1 point, several zeros and 1, and because p is more than 1, this series converges. Let's look at another example, summation 1 plus n divided by 4n minus 3. So in the roadmap that I gave you, this is, you can check for yourselves, this is neither an infinite geometric series, nor is it the series of the form where the general term is 1 by n to the power p. So what we'll do is we'll look at the nth term, which is 1 plus n divided by 4n minus 3, take the limit of the nth term as n tends to infinity, which is, I'm going to divide both numerator and denominator by n. So that's going to give me a 1 by 4, because 1 by n and 3 by n will tend to 0. So I get a 1 by 4, and because this nth term is non-zero, the series diverges. Similarly, if I have minus half to the power n, summation minus half to the power n, this is clearly an infinite geometric series, with the first term being minus half, the common ratio is minus half again, and this series will converge as the quotient, the common ratio k is less than 1 in absolute value, and the sum here is going to be again a upon 1 minus r, which you can check for yourself, is minus 1/3. We have this one more problem here, summation square root of 3 to the power 1 minus n. Now here I have simplified it a little bit, because this is clearly an infinite geometric series. So I can write this as summation 1 by root 3 to the power n minus 1. Okay, and the terms here are 1 plus 1 by root 3 plus 1 by root 3 squared, and here the common ratio is 1 by root 3. So clearly the series converges, because some mod k is less than 1, and the sum here is 1 upon 1 minus 1 by root 3. And this last part, this is a question, this is the last question I am going to do in this lecture. This is actually a question that illustrates the method of partial sums, so it's an interesting question. So let's suppose you have a series which is given by summation 1 by k times k plus 1, and this is the partial sum here, it's the first sum of the first n terms. So that's summation k going from 1 to n, 1 by k times k plus 1. So if you just open up this series, this is a finite series, finite infinite series. So if I put k equal to 1, then I am going to get 1 divided by 1 times 2, then when k is 2, 1 divided by 2 times 3 plus 1 divided by 3 times 4, and so on till 1 divided by n times n plus 1. We will just take you in the next step to an infinite series. Now the first part of the question asks you to prove that this partial sum can be written as n upon n plus 1. And then you can find the sum of the infinite series by taking the limit of this partial sum as n tends to infinity, and that is something we will do in the next step. So first of all, how can we show that S sub n is n upon n plus 1? For that, we are going to use this identity that 1 divided by k times k plus 1 is 1 by k minus 1 by k plus 1. You can check for yourself. Here the LCM is k times k plus 1, and in the numerator you will have k plus 1 here and k, so that is a k. K plus 1 minus k, that is a 1, exactly. So when we use this identity, my nth partial sum, summation 1 by k times k plus 1, where k goes from 1 to n, can be written as summation 1 by k minus 1 by k plus 1, if I use this identity that I just talked about in the previous slide. Now this we can write in turn, we can open up the brackets and write things as summation 1 by k, where k goes from 1 to n, minus summation 1 by k plus 1, where k goes from 1 to n. Let's expand for the different values of k. So when I have summation 1 by k, where k goes from 1 to n, this I can write as 1 plus half, where k is 2, plus 1 by 3 when k is 3, and so on till 1 by n when k is n. Similarly, 1 by k plus 1, when k is 1, you will get half. So we are going to subtract off this sum, half, and when k is 2, I have 1 by 3 plus 1 by 4 and so on till 1 by n plus 1 by n plus 1. Now, you can see here that very nice things just simplify. So, half will cancel out the half in the second bracket, 1/3 will cancel out the 1/3 in the two brackets, right. 1/4 will also get cancelled similarly, and so on till 1 by n will cancel out the 1 by n in the second bracket, and you are left with 1 minus 1 upon n plus 1, which you can see is nothing but n upon n plus 1. So, the nth partial sum, which is the sum of the first n terms, can be written as n upon n plus 1. Now, here why did we develop this? We want to ultimately find the sum of the infinite series. What if n tends to infinity? Can we find the sum of the infinite series where k goes from 1 to infinity? So, that can be easily done where we take the limit of s sub n, the nth partial sum, as n tends to infinity, and that is then the limit of 1 minus 1 upon n plus 1 as n tends to infinity. So, clearly when n tends to infinity, the second term will tend to 0, right. So, you are left with a 1, which is to say that where you are ultimately asked to find the sum of the infinite series, summation 1 upon k times k plus 1, where k goes from 1 to infinity. So, the partial sum there was n upon n plus 1, and when we took the limit of that partial sum as n tended to infinity, we got a 1. So, that will be then the answer for the sum of the infinite series. So, this is all I have for the second part of the video. If you benefited from, if you benefited by watching this video, please hit like, please comment, share and subscribe, because that helps us cater to the students better. So, that's all from me. Thank you very much. Bye-bye.